So we're going to discuss light and the electromagnetic spectrum. So when we talk about the electromagnetic spectrum, what we're really talking about is a whole host of different wavelengths. The wavelengths you can see with your eyes are what we refer to as visible light, and really run here from somewhere just underneath the ultraviolet all the way over to the infrared. So as you can see, the wavelengths you can see with your eyes are only this tiny amount of the electromagnetic spectrum. So this is visible light. All of this is high energy radiation from ultraviolet out to cosmic rays, and from here at the red end of the spectrum all the way out to radio waves is the long wavelength or low energy part of the spectrum. So this whole array of visible light fits into this tiny bit of the entire electromagnetic spectrum. So when we talk about light, it's obviously one of those things that we've been experiencing for the entirety of human existence. And as such, we have to start looking at it in terms of science. And some of Newton's work was some of the earliest attempts to really quantify light in scientific papers. So Newton was the first to really document the splitting of sunlight using a prism. So using a long triangular piece of glass, he would put this in his window, shutter his window, and then take a beam of light and split it up into its component wavelengths. It turns out when you refract light, and we'll talk about refraction soon, and you refract light twice, you change its speed, and you actually end up splitting up white light into all of these different colors. So when Newton did this, he saw a rainbow effect. And if you do this experiment, you'll actually end up with some heat generated here at the infrared end of the spectrum, and here you'll have your ultraviolet light just outside of the visible range. So here's essentially a modern recreation of Newton's experiment. Here is a white light source, here is a narrow slit taking our light source and making it into a beam. We then have a prism, and the light is split up into its component wavelengths and projected as a rainbow. And this is basically what Newton did, and here's a image from one of his papers where he took white light and he split up the white light into a spectrum and then recombined that spectrum, recombined all those different wavelengths and made it back into white light, showing that light from the sun was basically composed of light of all different wavelengths. I say white, the light from the sun really peaks in the yellow. Newton did have his challenges when it came to talking about light. And here's Newton actually a light. His little dog Diamond decided to jump up onto his desk and knocked over his candle. This resulted in setting fire to his entire set of optics notes and losing years and years worth of work. After this, Newton actually retired for 2 years and suffered a nervous breakdown due to the loss of these notes. So the sun essentially emits radiation across the entire spectrum, and this is what Newton was working with. Today, of course, we have white light sources that we can compose and project a specific wavelength. Sunlight is comprised basically of many different wavelengths of light. If you break it down, you can get your component wavelengths. The sun peaks at a wavelength, lambda, of about 501 nanometers in the yellow part of the spectrum. And this diagram is really showing us the spectrum yet again, but here it's comparing these sizes, the sizes of the wavelengths of this light, to the various everyday phenomena such as hydrogen atoms or football fields, and the uses of each part of the spectrum. This end is the short wavelength end of the spectrum, which means it has high energy. This end is the low energy end of the spectrum, long wavelength radiation. So far we've been discussing electricity, and we've discussed that at length. And we do kind of want to segue between discussing electricity and electromagnetism. And it was really Maxwell and Faraday that were the pioneers at this. Before this, no one really had a good idea exactly what light was. And it's Maxwell's equations that really lead us to describe light in its fullest way. So Maxwell's equations suggested that electric and magnetic field vectors could actually be put together, and you could actually describe light as a alternating electric and magnetic field. So he would look at charges and say, well, if you have some kind of current, the change in the fields relates to these quantities. So Maxwell's equations are fundamental to light the same way as Newton's laws are fundamental to our knowledge of motion. And Maxwell produced a wave equation for the electric and magnetic field vectors. Now, Maxwell's equations are slightly complicated, and manipulating them can be difficult. But I do want you to just realize what Maxwell's equations are. I will likely not ask you to actually manipulate or use them. But what Maxwell was really doing was explaining that if you accelerate a charge, such as an electron in a moving current, you will generate electromagnetic waves. So he could hook up an AC current to a piece of metal, essentially an antenna, and he could receive electric and magnetic signals from it. And this was his equation. He showed that the speed of light was basically 1 over the permeability of free space times the permittivity of free space rooted. And as I said, Maxwell's equations may be a little bit outside of the mandate for this course, so we can really express them as an integral, and you can relate essentially a magnetic field to a current, as we've said before. And it was Faraday's experiments that kind of showed this, and showed that Ampere's law breaks down a little bit, and Ampere's law is not perfect for systems such as the ones that Maxwell and Faraday were discussing. And this is where Maxwell's equations come from. And there they are, essentially different versions of Gauss's law for magnetism and Ampere's law for electricity combined together. And it's really those equations that really dictate how electricity and electromagnetism are interrelated. So electricity and magnetism, as we've sort of discussed before, are kind of different facets of the same thing. That's why they're combined into electromagnetism. A moving electric charge gives a magnetic field, and a changing magnetic field gives an electric charge. When we do this, such as when we turn on a solenoid, we actually emit radio waves. We actually emit electromagnetic radiation. And we've discussed this before in terms of charges being in motion and Faraday's law. So basically, a changing magnetic field gives a changing electric field, and a changing electric field produces a magnetic field. And electric and magnetic fields can produce forces on charges. So every time we accelerate a charge that's move an electron, say in a current or in a antenna, we will produce electromagnetic waves. And great pains are taken to insulate wiring so that things such as the wiring in your house that hooks up your lighting system shouldn't interfere with your, say, your sensitive internet communications. So both electric and magnetic fields transport energy. And interrelated electric and magnetic fields traveling through space are electromagnetic radiation. Something to keep in mind is that all electromagnetic radiation travels at about 2.99 times 10 to the 8, or if you're doing quick calculations, about 3 times 10 to the 8 meters per second in a vacuum. And this is going to be particularly useful when we start to talk about refraction. And 3 times 10 to the 8 meters per second is essentially the speed limit of the universe. And this image here is actually showing us, here's, say, a magnetic field and an interrelated electric field. One polarized one direction, one in another. In a little bit of background, for the longest of time people would argue about what's really waving in an electromagnetic wave, and this was really the forefront of late 1800s and early 1900s science, was what's the transport medium. If you take something like a sound wave, it requires an atmosphere, it requires gas, or it requires a fluid at least to travel through. But there are no sound waves in a vacuum of space. And by this point, people had figured this out. So how could waves travel through empty space? And the question really was, what is waving? And electromagnetic waves can indeed travel through empty space. And people felt that there might be a mysterious, unseen fabric called the ether. It now turns out this may not be the case, but ideas like this do frequently resurge in physics terms, though not in terms of electromagnetic radiation these days. But we'd had for a long time the idea that the ether was this fabric of space and a continuum which waves are traveling through. Turns out this isn't actually true. And electricity and magnetism are basically different facets of electromagnetism. The magnetic field induces the electric field, and the electric field induces the magnetic field. And waves can travel through, light waves at least, can travel through complete vacuum. They do not need any kind of medium that we really know of. So in terms of electromagnetic radiation, of course, we're not just talking about the light that we see with our eyes, but X-rays, gamma rays, infrared, that's heat, microwaves, cell phone signals, AM and FM radio, all of these things that we employ are extremely useful across the spectrum. So let's characterize the electromagnetic spectrum a little bit. There's a fundamental relationship for any wave between the frequency, the speed, and the wavelength. The speed of a wave tends to be given by c. C is usually the speed of light. You can use v here if you want to talk about the speed of a general wave which isn't necessarily light. But c, the speed of a light wave, should equal f, its frequency, times lambda, its wavelength. Different frequencies of electromagnetic radiation will travel at different speeds and have different energy. The frequency of your radio wave really determines its characteristics. As we discussed before, if we take our magnet and we put it through a coil, we can bounce that magnet up and down and we can generate a current. So as this magnet moves through this wire, the current, the charges in this wire will move, they will feel a force, and that will generate what we refer to as a current. Now, every time we do this, not only do we get moving charges, those moving charges produce electromagnetic radiation. So if you do this experiment and you move the magnet through the coil, you're essentially also producing electric and magnetic waves at the radio wavelength, which will be traveling through space. So you can actually manipulate this by accelerating the charges in a piece of metal, and this is essentially a transmitter, or at the other end, a receiver, an antenna. So accelerating the charges in a piece of metal will produce electromagnetic energy. So if we hook up our piece of metal to an alternating current, that will result in the charges, the electrons specifically, being encompassed by an electric field in one direction, and then as the alternating current switches, it'll experience an electric field in the other direction, moving the charges up and down this conductor. So if we're to generate radio waves, we apply an electric field one way, we'll get a radio wave, and then we can reverse it and apply the electric field the other and get another radio wave. And this is basically the way in which radio transmitters work. Applying an alternating current that comes from a microphone as you speak will jiggle, essentially, the electrons at the correct frequency. That frequency can then be received by an antenna and translated back into sound. So this is the connection between electricity and electromagnetic radiation. So the charges will oscillate back and forth, giving time-varying magnetic fields. If we have a transmitting antenna, we can essentially jiggle our electrons in that antenna at a specific frequency and give out radiation of that frequency. If you look at a radio set, usually you'll find it says something in the gigahertz to megahertz range, depending on if it's AM or FM. Digital radio works on a slightly higher frequency. So if we jiggle our electrons, we will get radiation at the frequency at which we're moving our electrons up and down. That's our transmitting antenna. We'll end up with waves moving out in some direction of E cross B. If the electric field is 90 degrees to the magnetic field, you'll end up with a direction of propagation, essentially in a straight line, 90 degrees to the two of them. Now, when we tune a radio, what we're essentially doing is jiggling our electrons in this antenna at the proper wavelength. So when we tune them to the wavelength of the signal, we give them a specific polarization, a specific susceptibility to be jiggled at a specific frequency. And that's what tuning a radio essentially does. I realize jiggled is not exactly the most scientific term. So as the electromagnetic radiation passes through the antenna, it jiggles the electrons at a specific frequency, and only that specific frequency, and translates your electric and magnetic wave back into sound by using a speaker. And essentially, by manipulating our electric and magnetic fields, we can therefore send out signals as we wish. Those signals, of course, propagate out in an almost spherical pattern from our antenna. This actually influences the shape of an antenna. If you think about an antenna, car antennas used to be long, straight pieces of wire. You had such things as rabbit ear antennas for TVs, or circular antennas. So a loop antenna detects electromagnetic radiation, because what you're really doing with the loop is attempting to maximize phi, maximize the flux through your antenna and jiggling as many electrons as you can. So in terms of generating radio waves specifically, things do get a bit complicated. These are the frequency allocations by the FCC for all of the different parts of radio transmission. And as you can see, this is how things are divided up for different purposes. So science and radio navigation and things like that get 399.9 to 400.5 megahertz here, and TV broadcasting channels get a massive chunk here from 512 to 608, truly showing where people's priorities are. Radio astronomy is relegated to this tiny little band over here, and this is getting ever more complicated. And of course, internationally, different countries actually allocate different proportions of radio signals for different purposes, so things get difficult as you move from one place to another. Just for reference, a frequency of 300 megahertz here has a wavelength of about 1 meter. So what does this mean for modern communications? Well, if you ever smash your cell phone to bits and have a look inside of it, those who no longer have a long antenna sticking out of the top. Think of a cell phone from the 1980s or even the 1990s or early 2000s. It still had a stick antenna out of the top of it. Your modern cell phone tends to use a fractal antenna that is integrated into the back of the phone, and that's why our designs have changed. There was a time when cell phone companies were competing, and there were many different designs, some with antennas, some without. Now, since the fractal antenna has come in and people have employed that by just really sticking it behind the screen, we end up with every phone looking like the same old brick with a screen in it. But this does make them more compact and square. In terms of our discussion of light, we're going to really go into talking about light and how to manipulate it itself in terms of optics in our next section. However, radiation itself does actually exert a bit of a mechanical force. It's not strong, but it is there. And as such, there is the effect called radiation pressure. Now, electromagnetic waves carry energy, but they also carry a bit of momentum. And that can really be described by the intensity of your wave. And that's the power per unit area that's incident on a surface. So if we go back to mechanics, momentum essentially would impart velocity to an object. And momentum is mass times velocity. So radiation actually exerts pressure on an object when it hits it. So a charged particle essentially experiences a force as it hits an object and gives us a velocity. You don't necessarily need to use this equation here. We're essentially just substituting in for the acceleration of a particle, and that'll actually translate kinetic energy to an object. What does this mean for us? That means that momentum, P equals mv, can be given to an object based on just light hitting it. So essentially you can power a sail using light if that sail is big enough and you have an intense enough light source. So momentum here is essentially intensity divided by the speed of light. This is potential energy here over c, which translates the intensity of light. And in this way, you can actually use this to sail around the solar system. Light can come in from the sun and hit large reflective sails and propel a spacecraft around the solar system. If you're anywhere near a particularly intense star, you can use this radiation to essentially drive yourself around that system. It is a little difficult. You would have to essentially sail using these, but you can use momentum from starlight to do this. So let's take a look at an example. Here we have a 50-watt light bulb. Now a 50-watt light bulb will emit spherical electromagnetic radiation in all directions. We're going to find the intensity of the bulb at a distance of 3 meters and the radiation pressure that we will get from a single light bulb. Now remember, we have a power here of 50 watts. And we're looking at a distance of 3 meters. Our equation for radiation pressure is essentially P equals I over C. At some distance, the energy is going to be spread out over a sphere. It did say it was coming out in a spherical pattern, so we'll have to take our radius as being 3 meters, and we have to look at a sphere of area 4 pi r squared. So that's the area of a sphere. So the intensity will wind up being 50 watts, which is the power of the system, over 4 pi r squared. So we're rearranging P equals I over C here. So we end up with 50 watts over 4 pi times 3 squared. This will give us 0.44 watts per square meter. What we really cared about was what is the radiation pressure from the bulb here. Well, the radiation pressure, P equals I over C, is going to give us 0.44 over 3 times 10 to the 8. This will be 1.5 times 10 to the minus 9 pascals. That's a very small pressure. But of course, a light bulb compared to something like the sun has an extremely small intensity. So that characterizes light a little in terms of segueing from electricity into our discussion of light. But what about light itself, which is where we're going in terms of optics? As we've already said, light is electromagnetic radiation. Light travels as what we call photons. A photon has sort of a dual behavior. It has a bit of a split personality, and it behaves as a wave, but it also behaves in many cases as a particle. But basically, all electromagnetic radiation will transfer energy from one location to another through alternating electric and magnetic fields, as we saw previously. So here is a single photon. It will have a wavelength where we can go from, say, the peak to peak, or from the trough to trough to find that, and it will have a frequency. That's how many times is this wave repeating in a second or some other given time. So a wave is basically referred to as a rhythmic disturbance that transfers energy. And all waves, as we discussed when we talked about electrons vibrating, essentially oscillating in an antenna, are made by something that vibrates. As we said previously, mechanical waves need matter to travel through, something like a gas or a fluid, whereas something like light can travel through basically empty space, through a vacuum. And there are two basic types of wave. You have transverse waves, which are really the form that light takes, which have crests and troughs, and you have longitudinal waves. These are compressional waves, such as sound waves, which are made of compressions. Here's a compression, and essentially expansions, or what are referred to as rarefactions. And they are controlled by the equation we discussed before of C equals F lambda. Sometimes you might see this written as nu, but that's a terminology I don't particularly like. I like to use frequency as F where possible. And here's a transverse wave. Here's an object that's jiggling up and down, such as an electron, and here's a wave being produced by the motion of that electron. Longitudinal wave, here we have a collision here, and this pushes essentially the wave by compressions and rarefactions down the line, such as a sound wave. So in dealing with a transverse wave, such as light, we can see that we have our peaks and troughs in both the electric and magnetic field components of our wave. The wavelength will be the repeating point from peak to peak or trough to trough. The wave travelling in this direction in this particular diagram will also have its frequency of how many times it repeats in a given time, usually given in hertz or inverse seconds. Our longitudinal wave, of course, is shown as compressions and rarefactions, such as air molecules bouncing in and out in this particular respect. Now, in this particular case, you can mathematically model the compressions and rarefactions, of course, in terms of along a transverse wave. So here we can see our wave shown as per the light wave, but of course physically that's not what's going on. This is merely the harmonic that's used to express this physical wave, giving us our transverse and longitudinal waves in comparison, both using the same equations of C equals F lambda and E equals HF, however both from a slightly different perspective. If we're concerned with light, we'll be sticking to essentially the transverse case. So, in terms of the properties of a wave, we have the wavelength and we have the frequency. There are three basic properties of light. You have intensity, you have frequency, which is related to the wavelength, and you have polarization. Frequency is the amount of times an event is actually repeated. So the frequency of electromagnetic radiation is the number of times a wave repeats itself. And this is usually measured in hertz, or Hz here. 1 hertz equals 1 cycle per second. Sometimes you even see this expressed as inverse seconds, s to the negative 1. Either unit is acceptable, but hertz tends to be the often quoted unit, and that's why you see such things as radio waves in terms of gigahertz and megahertz. Millions and billions of cycles per second. So as we said before, the speed of light, c equals f lambda. C in a vacuum is 299.793 times 10 to the 6 meters per second, or about 3 times 10 to the 8 meters per second. Now, waves will behave differently in different media. That means sound is faster in more dense media and in higher temperatures, and light is slower, also slower, in more dense media. So light is kind of the opposite of sound. Sound requires particles very well packed together to more easily translate its mechanical wave. Something like light moves faster when there's less material around, where there's less things for it to bump into and interact with. So wave velocity really depends on the type of wave and the medium. So as we're discussing light, you will end up with values of c, 3 times 10 to the 8, simply in our vacuum. Any other medium, you will end up with a different speed. And that's why we ended up with, say, the electromagnetic spectrum, as Newton's experiment showed us, breaking down into its component wavelengths as the different wavelengths travelled at different speeds through his piece of glass. When we deal with the speed of a wave, we can analyze it using what's called the Doppler effect. Now, I'm going to discuss this in terms of sound mostly, but the same thing will occur with light, and I'll explain that effect after I've used a sound example that might be more typical in everyday life. So think about an ambulance travelling down the street. You should notice that the pitch of the ambulance changes as the ambulance moves. As an object is moving towards you, you have a higher pitch, and as the object moves past you, you have a lower pitch. It's in this way that police radar guns will actually measure your speed, and also you often see on TV stations when they're discussing the news how they have ABC TV's super hyper mega Doppler radar and all sorts of other things added to the beginning of Doppler that don't really make sense. That's really just sending out a radio signal, bouncing it off a cloud or a storm, and getting that radio signal back. And from that, you can determine the speed of, say, a storm or a cloud moving across the country. This is used in astronomy a lot in terms of looking at the wavelength of light from stars and galaxies and calculating the speed of those objects. So in terms of the Doppler effect, and once again, please don't go and stand on a train track in order to see this effect. If we have a train standing still here and two people, one standing here and one standing here, both of them will register the same pitch sound from this train. If the train is moving with some speed, as it moves towards this person over here, they will actually receive a shorter wavelength of sound from this train, a shorter wave, so they will register a higher pitch sound. This person will hear a lower pitch sound. So even though the train is putting out the same wavelength of sound wave throughout its motion, two different observers will hear it differently and register these waves differently due to the train's motion. The same thing happens with light. However, taking a light bulb and running across a football field with it will not show it moving towards the blue or red ends of the spectrum. A light source has to be moving much, much faster than say a source of sound. The speed of light's only in the hundreds of miles per hour, whereas the speed of sound is only in the hundreds of miles per hour, whereas the speed of light is in the 10 to the 8 meters per second category. That means you have to move a light source very, very, very fast to actually observe this effect. So basically, when an observer moves with some speed, v0, relative to a stationary source, the frequency you will receive, f prime, will be the original frequency of the radiation times 1 plus or minus the original velocity over the velocity of the observer. That's relative to the observer. The plus or minus really denotes whether your object is moving towards or away from you. This can also be, of course, expressed in terms of the observer or the actual object itself. If both the source and the observer are moving, you do have a situation where you have to figure out your plus and minus signs. The upper signs, the positive V0 and the negative Vs, will refer to the motion of one toward the other, and the lower signs refer to objects moving away from one another. So if the objects are moving away from one another, you'd have V minus V0 over V plus Vs. If they were moving toward one another, this would be V plus V0 over V minus Vs. So there is some thinking to be done in employing this formula. And definitely read through this section of the book on how to utilize the Doppler effect. So as an example, here we have an ambulance, well actually Ecto 1, travelling down a highway at 33.5 meters per second. Its siren is emitting sound at 400 Hertz. So F here is 400 Hertz, 400 cycles per second. What's the frequency of the sound heard by a passenger in a car travelling the opposite way at 24.6 meters per second? So the ambulance is moving at about 34 meters a second from the left to the right, and the car is moving at about 25 meters per second from the right to the left. We have the frequency of the sound wave, and we want to know what's the frequency of the sound heard as the car approaches the ambulance and as the car moves away from it. So as the car moves towards the ambulance, we're going to say that f prime, the frequency of sound heard, is going to equal the original frequency of 400 Hertz times v plus v0 over v minus vs. We have these velocities we can substitute in. We have our 400 Hertz. That will give us 475 Hertz. So as the car approaches the ambulance, the people in the car will hear a higher pitch. This is shifted towards the higher frequencies for them. As the car moves away from the ambulance, the two of them are receding. So now the frequency they will hear, f prime, will be equal to f v minus v0 over v plus vs. Think about the signs that need to be employed here. This will equal 400 Hertz again, times 343 minus 24.6 over 343 plus 33.5, and give 338 Hertz. That will result in a lower pitch. When we're talking about light, this is particularly useful to astronomers because the spectrum of an object will be changed due to its movement, and stars and planets even are moving quite quickly. When we're dealing with stars, if an object is moving towards us, it appears bluer and is what we call blue shifted. If an object is moving away from us, it moves towards its color moves towards the red end of the spectrum, and is what we refer to as red shifted. The greater the shift, the greater the speed. And if we take spectra and we actually look at spectral lines in a star, we can say that, well, in a lab we end up with a wavelength through a particular line from a particular chemical constituent in the star of, say, 500.7 nanometers. If we measure that same line in a star, we end up with a lambda, a wavelength of 502.8 nanometers. The wavelength from that star's spectral line is longer than we would expect. That means the star is redshifted. So stars that move away from the Earth will appear redder, even though stars themselves may already be a bit red, and stars that move towards us appear bluer. And this is kind of a question when you look into the sky of, a lot of the time, is this a particularly blue star, or is it moving towards us particularly quickly? Or if it's redshifted, is it moving away from us particularly quickly? The effect with stars is less pronounced than the effect with galaxies, which are moving very, very fast. Now please ignore the fact that Mars goes around on its poles here, but I didn't actually get an equatorial rotation. So Mars is moving on its poles, but it's really the example that we care about. So if we look across, say, a planet, we can look at one side of the planet and see that it's redshifted, the other side will be blue shifted. And using radar and using lasers, we can actually figure out the rotation rate of a planet by the blue or red shift across its disk. Frequency, as we said, is the amount of times our event is repeated. We just manipulated our wavelength. Here we just want a reminder of the frequency, and this was given in hertz. And our frequency is essentially related to our wavelength in an inverse state. Now, as mentioned before, by c equals f lambda, this is the speed limit of the entire universe. So when you are doing calculations, please make sure that your calculations never exceed 3 times 10 to the 8. This does also mean that science fiction spaceships and traveling much faster than the speed of light is completely impossible. There may be ways to travel long distances by circumventing that, but you cannot travel faster than the speed of light, or even actually at the speed of light. We've already discussed the intensity of radiation, but the intensity, when we're actually examining a wave, is essentially the amplitude of our wave. That's the height of the wave if we look at it as a plot from a central 0 point. So the amplitude is essentially half the distance from the trough to the peak. So if we were to find the intensity of this particular light wave, we would measure its amplitude, which would be the height from this 0 line to here. If this is a regularly repeating wave, we could essentially measure it from here to here. The intensity of a light wave actually drops off as 1 over r squared. Try shining a flashlight straight downwards and then shine it forward ahead of you at an angle. When you shine it ahead of you, you'll see that the light ray actually is much, much bigger than if you shine it directly at your feet, where it's much more concentrated. The intensity at longer distances is reduced by 1 over r squared. So here's our radiation source. As we get progressively further away, the same amount of radiation is spread over a bigger and bigger area. So here we are at a radius r. At 2r it'll be spread over 4 times the area. At 3r it'll be spread over 8 times the area. It's 9 times the area, I apologize. Now, the energy of any particular photon was one of those things that really wasn't particularly calculated until the era of quantum mechanics, and with people such as Planck coming up with his constant. If we're to calculate the energy of a light wave, we really need to take into account how much energy is being delivered per second. which essentially relates to the frequency of our wave. So the energy of a light wave is E equals h times f. Planck's constant of 6.626 times 10 to the negative 34 joule seconds times the frequency. And that, of course, will give you an answer in joules. This simple relation means that the energy is proportional to the frequency. That means the shorter the wavelength, the higher the energy. The greater the frequency, the shorter the wavelength. Because our energy is measured in joules, if we take something like a light bulb, which essentially is about 60 watts, you could say a 60 watt light bulb will use 60 joules of energy every second. So in terms of light, let's take a look at a problem. Light of wavelength 450 nanometers is traveling through space, essentially empty space here, a vacuum. What is its speed? What is its frequency? And finally, what is its energy? Part A, from what we've discussed so far, should be incredibly simple. What is its speed? Well, space is a vacuum, and we've already made the statement several times that the speed of light in a vacuum is essentially 3 times 10 to the 8 meters per second. So we should know the speed of this light wave immediately without any calculation. Part B said what is its frequency? Well, we just said that it's a light wave traveling through space, so we said that its speed is about 3 times 10 to the 8. We can say c here is equal to f times lambda. That means f is c over lambda. We're given the wavelength of c here in the problem of 450 nanometers already. Simple substitution, essentially 2.99 times 10 to the 8, to be a little more accurate, over 450 times 10 to the minus 9, remember this is nanometers, so we have to translate that to meters, will give us 6.7 times 10 to the 15 hertz. So have an idea about what kind of numbers should come out of this formula. 10 to the 8 is relatively high, 10 to the negative 9 relatively small, so frequencies of about 10 to the 15 are not unreasonable. Part C, what was the energy of our photon? Well, in part B, we calculated f, the frequency, so we're now armed with that. We can say, using Planck's constant, that E is equal to h times f. Substituting in, we will get an energy of about 4.4 times 10 to the minus 17 joules. Remember, this is the energy of a single photon. So the kind of values you should expect to see will be quite small. Even though we're talking 10 to the 15 hertz here, which is quite a lot, Planck's constant is very small, 10 to the minus 34 meters squared kilogram per second in magnitude. So remember, when we're talking about light waves, they can be across the spectrum, visible and invisible. And light carries energy and is essentially radiative energy. Put out your hand when it's on a particularly sunny day and sunlight will feel warm as infrared radiation is translated to your skin and starts moving these molecules in your skin around. The warmer you feel, the faster the molecules in your skin are moving and the greater their kinetic energy. So that infrared part of the spectrum is here, from about 1 to 100 microns. When you're down here, you're at the high energy, low frequency, high energy, low wavelength. Over here at long wavelength, you're at the long wavelength, so you're looking at low frequency, low energy. This stuff down here is the stuff that will penetrate matter and essentially move through you and give you cancer in a lot of cases by breaking up your DNA. If we look at the Earth's atmosphere, there's only parts of it where we can see completely through it. In the visible, some in the radio, and a little bit in the infrared. So a lot of repetition here, but as we said, light travels as photons, but also travels as a wave and a particle. So light actually has wave-like and particle-like responses when it impinges on a surface. That means that it can often behave like a hard sphere and bounce off of something, but it can also be absorbed in the same way that any wave can. And this is referred to as wave-particle duality, where photons behave as packets of light, and each little packet can have a specific wavelength and frequency. They are also referred to as quanta in this case, and this is where terms such as quantum mechanics are derived. And it was the 1800s where people like Thomas Young were doing experiments and showing that light was a wave, essentially putting two light sources together, A and B, and then seeing constructive and destructive interference patterns from the two wave fronts merging together, light and dark bands that he would form on a screen. Later on, when people such as Planck and Einstein were doing their calculations and doing their work, they proved that light was also behaving as a particle would. So it has this dual nature to it. Why am I mentioning this again? Because we mentioned this previously. Well, this turns out to be particularly useful in a lot of modern devices, especially modern cameras. Traditionally, for hundreds of years, people used cameras that used chemical processes, and the light would hit a chemical film and would develop that chemical film and then show different intensities, different colors, which could then be developed as a picture. Now, just take a look at the back of your cell phone. We have cameras that actually just use solid state devices. They use a chip. Radiation hits that chip, and then we can look at the radiation hitting it and we can form an image. And as we all know, this is increasingly popular and features in many devices today and allows you to track celebrities with ease. So inside your camera there will be this chip, and the radiation will go through a lens as per the old film cameras still, and that lens will concentrate the light and focus it onto the chip. This means that you can immediately make an image and send it straight to an electronic screen and see it in real time. So it was de Broglie and Planck and Einstein that expanded this to matter. And how did they do this? Well, they came up with something called the photoelectric effect, and this is one of Einstein's papers. Here we have incoming radiation, and we have a piece of metal. Light of a specific energy, in which we know energy will be equal to hf, can come in and hit this metal, and it will provide energy to the particles inside the metal, and it can eject electrons or make electrons mobile within the metal. And it's this particular effect, this particular behavior, that we use in all of our modern solid state cameras, such as those in your phone. And the equation was really, well, what is the maximum kinetic energy that a particle, that a charge, essentially an electron in a piece of metal, can have before it completely discorporates and flies out of that piece of metal? Well, that comes from Kmax. The maximum kinetic energy that an electron in a piece of metal can take is the energy of the photon, hf, minus what's called a work function. And this work function is essentially an energy to beat. This is essentially the energy limit you have to beat with hf to make it leave a piece of metal entirely. So it really just becomes a difference. The maximum kinetic energy of any electrons that fly off a piece of metal are essentially going to be hf minus phi, an energy of the photon minus the energy you need to beat of the metal, the binding energy to that metal. And essentially this is how CCDs operate. A CCD is a charge-coupled device. That's the kind of chip you have in an electronic camera. Radiation, here says h mu, but hf comes in. We have some kind of silicon wafer here, and then you have another type of silicon which allows your electrons to be mobile. The radiation comes in, hits the electrons, and allows them to be mobile, starts moving them around on the metal. Different voltages here will essentially collect the different electrons, we've talked about potential difference at length, or move them to the contact that they need to be at, count them, and then turn them into an image. So for instance, if one particular region of the image is blue, it will count all of the electrons of a specific wavelength and translate that to blue through E equals hf. The different energies can be translated to different colors. And in that way, we can move our image, we can move our charges that make our image from one place to another. So we can manipulate them via their voltage and create essentially an image based on electrons. So let's take a look at an example. So here, light with a wavelength of 240 nanometers is shining on a metal plate. Electrons will be ejected from this plate at an energy of 1.4 electron volts. Our questions are, what is the energy of the photons in the beam? What's the maximum kinetic energy of the emitted electrons? And finally, what is that work function, phi, for the metal? So initially we want to find the energy of the photons in the beam of light. We're presented with a wavelength of 240 nanometers and a energy of 1.4 eV. If we assume that the light is traveling essentially as in a vacuum, we can state that C is equal to F lambda. This is a reasonable assumption even if we're dealing with light traveling through air, as the speed of light through air is not appreciably different to a vacuum for our purposes. So we can say that F is C over lambda. This is essentially 3 times 10 to the 8 over our 2.4 times 10 to the minus 7 meters. This is a 240 nanometers converted. This will give us a frequency of 1.25 times 10 to the 15 hertz. This frequency is in hertz. We want an energy. We want that energy also in EV. So our energy is equal to h times F, Planck's constant, times the frequency, which is 8.275 times 10 to the minus 19 joules. This is an energy in joules. In electron volts, we can convert this by taking our value here and dividing by the electron volts of 1.6 times 10 to the minus 19 joules. That will give us 5.17 eV. Part B wanted to know, what is the maximum kinetic energy of the emitted electrons in electron volts? Well, our electrons are emitted essentially because the electrons come off of the plate. The question itself says that light with a wavelength of 240 nanometers hits the plate, and electrons are emitted from the plate with an energy of 1.4 eV. Consequently, the maximum kinetic energy of the emitted electrons is just given in the question, and they are emitted at 1.4 electron volts. Finally, part C asks, what is the work function of the metal? What's the energy we need to beat in electron volts to actually eject particles from this metal? Remember, phi was hf minus k max here. So what we're going to essentially say, since we've rearranged this for the work function, is this will be 5.17 eV minus 1.4, giving us 3.77 eV. About 3.8 electron volts is required to emit electrons from this plate. So here's a bit of summary on that section involving waves. And remember, just because of the things we were discussing, we were looking at wavelength, we were looking at frequency. There's one more property of light I want to discuss, and that's polarization. And this describes the direction of oscillation of the light. Here, the light is what we can call unpolarized. This means this light is composed of light that's all sorts of different orientations. Light here is traveling in this plane, and this plane, and this plane, and this plane. If we look at polarization, what we're essentially talking about is what's the direction of oscillation 90 degrees to the direction of travel. So our wave is going this way towards this filter, and we're looking at our wave in all different directions. As the unpolarized light beam hits this filter, which is a vertical slits, very, very finely machined, all the light that is polarized in all these other different directions will be blocked by this filter, only allowing the vertically polarized light to come through. Additionally, we could take a polarizer of the same type then and place that sideways, so now the polarizer is horizontal in case 2, and block all of the light. So in using different filters and different polarizations, we can actually filter out light of different polarizations that we want. This can be used in things like polarized sunglasses to reduce glare, or to create coherent light that we can use in various experiments and industrial processes. Where can you see this effect? Well, wear a pair of polarized sunglasses and say look at a windshield. Sometimes that windshield will appear dark in parts because of the polarization of the glass. Additionally, take out your cell phone, probably not one that's this old, and wear polarized sunglasses. You should be able to turn your phone to a specific angle where the screen will go black. This is because LCD screens have a specific polarization. The light coming from them is polarized, and if you turn your filter to the same polarization, you will essentially block the light and see a black screen. The effect can also be seen wearing polarized sunglasses and looking at an LCD computer monitor. Rotating your head, you should eventually see that the screen becomes black. This is the kind of thing that's used in privacy filters to prevent people from looking at sensitive information in offices. So in terms of polarization, how can you polarize light? Well, reflection changes the polarization of light. So here we have a glass block. Light is coming in, unpolarized light, oriented in all different directions. As it hits this particular block, the light will bounce off. It will be reflected. The reflected light will be polarized in one specific direction. And this is a way of telling the difference between transmitted or refracted light and reflected light, as reflected light will be polarized in some fashion. We're going to talk about refraction later on, but if we take any piece of glass or transparent material and shine light upon it, some light will be translated through the object, such as looking at a window. Some light will go through, but you'll see your reflection coming back. The refracted ray here, or the light ray going through the block, will essentially maintain its polarization, but the reflected ray will not. But any ray can be partially transmitted, this means travel through the object, and partially reflected, bounced back. This is why when we look out into space and we look at things like nebulae, floating clouds of gas and dust, they appear this whitish colour. So all of this whitish material, as you see here, is reflecting light. It is not emitting its own light. The pink material is doing that, but the white material is essentially just reflecting light. Additionally, this isn't empty space. This is very, very dark dust absorbing light. Which leads us to our, essentially, one of our final sections. In terms of light and matter, there are 4 ways that light and matter interact. Light can be emitted, such as a light bulb or the sun. Light can be absorbed. That means take an object, put it near a lamp, it will warm up. Light is also transmitted, as we've discussed in one of these previous slides, where some material will allow light to pass through, it's transparent, and others will not. And then you have reflection and scattering that we just discussed, where light bounces off an object. Most objects will absorb and reflect light in some fashion. Everything you see with your eyes that is not emitting radiation, such as maybe a table in front of you or a wall, is essentially reflecting light and not emitting it, unless of course it's on fire. So here we have a situation where the sun here is emitting light. That light is coming down, hitting bright snow, which is reflecting light back. If the sunlight hits a tree, for instance, all wavelengths of light will be absorbed, but green will be reflected. Plants absorb what they need and throw the rest away. So plants essentially are not using green light to photosynthesize, which is why they appear this color. The dark ground will absorb radiation, which will go into heating it up. Here we have a very finely dressed man in a particularly bland room. He's sitting here looking through this glass. Light is traveling through the glass, so it's essentially transmitted, hitting him and his wonderful blue vest, and essentially every other wavelength of light is being absorbed apart from blue, which is bouncing off of him. Of course, his eyes will absorb light and allow him to see and perceive light. His red chair absorbs everything except red. He has a light bulb in here in his wonderful stylish lamp that is sending out radiation and emitting radiation, and a mirror which reflects light. So in this example, we're seeing all of these things at work. We can use these kinds of principles in investigations scientifically in such cases as a spectrograph. In a spectrograph, we're essentially capturing light and then breaking it down using a prism into its component wavelength. Most spectrographs these days don't use a prism so much as a grating, quite often a holographic grating, to break down the light. And when we do this, we can produce spectra. And we can do this in the lab, we can do this with telescopes. There's a lot of different applications for looking at the spectrum of a source and figuring out the atomic and molecular components of a particular chemical. So the radiation from a source will have distinct light patterns within it based on the energy levels of the ions or molecules that we're actually observing. These different light and dark patterns are actually a result of transitions of electrons or energy levels of particular molecules. So if we take something like a molecule, as it rotates and vibrates, it will have a specific energy. As it loses that energy, its molecular vibration and rotation will reduce, and it will end up emitting radiation in the form of a photon, which we can then detect and then characterize this molecule in terms of its dynamics. These can often be quite complicated. For instance, here is doubly bonded hydrogen, just a diatomic molecule, which essentially behaves just like two masses on a spring. And as you can see, just for H2, these are all individual lines. This block of light is minute spectral lines. But this would essentially be the chemical signature of H2 if we were to see that in the universe, or see that in a biological sample inside, say, some kind of spectrograph in the lab. So that's one use of spectra, of breaking down the light and looking at specific signatures of different particular materials, and in doing so we can figure out such things as the constituents of the stars and the constituents of samples within a lab. By knowing the atomic number, we can figure out the different energy levels and the different patterns of light that we should see. By comparing that to the periodic table, we can of course identify our different components, our different atoms, our different molecules.